Okay, folks, we're going to start this chapter, chapter 3, which is an introduction of organic chemicals. And what I mean by that is it's basically just that. It's a very basic opening to everything that is organic, so any molecule with a carbon in it. And we're going to focus a little bit on nomenclature and just alkanes, or simple hydrocarbons. All right, first thing we're going to talk about is the diversity we get in organic chemistry, because while organic chemistry is the study of things just with carbon in it, as soon as we add other things to it, we actually drastically change the chemical properties and chemical behavior. But it gives families based on those chemical behaviors are controlled by what the actual atoms are. Like, for instance, the alkanes, those are just carbons and hydrogens. Now, specifically, it's all carbons and hydrogens where there's nothing but single bonds. So I'm going to put CHs and then singles. And typically, these alkanes we're going to see get listed as just Rs. So like an alkyl halide, we're just going to take that alkane, or those carbons and hydrogens, and connect them to a halogen, like maybe chlorine. Or what we see happen is we end up using the letter X to represent any of the halides. Next little chemical diversity family they're talking about is the ethers. That's where we take our organic compound and connect it to an O, but on the other side is another R. Might be the same exact one. The most common ether, which actually gets the name just plain ether, is actually diethyl ether, where each of these R groups are just two carbons. Next family is alcohols. Still got that R on it, but instead of an R on the other side of an O, it's actually an H. And then amines are anytime that R group is attached to a nitrogen, and these other two positions off the nitrogen can be just about anything. And there's plenty of others. And we're going to see all of our main functional groups in this chapter, and we're going to introduce ways, or the basis of how we would name any organic molecule based on those functional groups. All right, but we're going to start with the simplest organic family, the alkanes. Now, hydrocarbons is an additional name for this, but not all hydrocarbons are alkanes. Hydrocarbons are just things that are made out of hydrogen and carbon. And the reason alkanes are hydrocarbons, because that's all they are. That's what this table lists over here, is the various different simple alkanes. Now, to be an alkane with that as an A, you can only have single bonds. If there is a double bond in there or a triple bond in there, it's no longer an alkane. And because of that single bond rule, we can actually kind of say that all alkanes follow this nice little rule, that if you know the number of carbons, the number of hydrogens is twice that plus 2 always. Now, what we end up seeing a lot is this little expansion on our condensed structure where they got that little sub N, tells you that that middle CH2 is repeating. And you see that we're doing that a lot on this table here to the right there. And that's simply because that bottom one with 30 carbons, if we were to draw this thing to scale, that structure there would have 30 carbons, 62 hydrogens, all done in that condensed formula. That would have taken a lot of space. The table would have been about, 3 feet long? It would have been huge. So using that condensed structure can speed up the time. Now, what else they have on there? They have density, they have boiling point, they have melting point. And as you'd expect, the boiling point and melting point go up, and that would be related to the molecular weight, because all of these are going to have just dispersion forces. So that would explain why they increase. All right, and our simple alkanes, the 4 simplest ones, have these common names that are also the standardized names: methane, ethane, propane, and butane. And along with the name, I have the calculate structure, which in this case is a Lewis structure. And then next to that is the condensed structure. And then we have this ball and stick method. That's really going to come in handy as we go into some of the later stuff, because seeing the physical shape of the molecules helps us see, or at least imagine, what's going on at the microscopic scale. All right, And my next little thing, we're going to talk about how we can change those positions. We call it constitutional isomers, because what I can say here, these two up here are actually both constitutional isomers, because if I were to reduce it to a simple molecular formula, you notice both these have 4 carbons. And if you count them all up, you're going to find out that both have 10 hydrogens. So what we're saying is a constitutional isomer is 2 different molecules that have the exact same molecular formula. And it should be 2 or more, because right down below here, I have all these constitutional isomers of C5H12. Now, obviously, they're not the same molecule, and we do know from that previous slide this thing was actually called butane, but that's the only one of these that we actually have a name for. Now, turns out once we get past butane, the prefixes start to make a lot of sense, and since this is 5 carbons in a row, pent-ane. Now, the other 3 on this page will have a different name, but the straight chains really are just named based on how many carbons they are in a row. But that's where this gets to be more complex, because naming our constitutional isomers involves quite a bit of complexity, and that's what we're going to be focusing on here next, because right here we have a huge number of constitutional isomers. I got a bunch with just 6 carbons, and I have a bunch there with 7 carbons. Now, all of them, or both of these sets, so I'll put this group in parentheses, these all have the exact same molecular formula. There are 6 carbons, and there's twice that plus 2, so 14 hydrogens. And down here, all of these have 7 hydrogens, or 7 carbons, and 16 hydrogens. And they're just put together differently. Now, the only ones that have straight, simple names are the 2 straight line ones. This straight line one, 6 carbons, hexane. And this straight line one with 7 is heptane. All right, if you actually just came out of general chemistry, there's a good chance we talked about naming organic molecules, and we created a basic set of rules that we actually did. What we were going through was the IUPAC names. That's the most commonly used names. It's uniform, it's systematic, it follows a very clear set of rules. Common names don't necessarily do that. Common names are typically, in a lot of cases, just ones that have a little bit of history to them, and they've been used. Now, common names are not typically things that we ever test on, and for the most part, it's safe to say in Chem 1, if I give you a molecule with its common name, it will also have listed its IUPAC name. IUPAC name is a little bit more useful for us in Orgo 1. In your textbook, the Brucey textbook, the common names are typically listed in blue. Or no, IUPAC names are listed in blue. All right, now, back in Chem 2, you might have had an introduction of organic chemistry, and we had a very basic set of rules that involved naming your compound based on finding the longest continuous chain of carbons. Turns out these rules that we got in general chemistry, and this is a different book, but it is the same thing that we did in OpenStax at our book, but rather than saying this was the rules for naming organic compounds, this was the rules for naming hydrocarbons. Because it turns out when we add those functional groups to it, the rules change drastically. Matter of fact, the priority or which functional group is present is more important than the length of carbons. So what I mean by that, see how these things are ranked, and you notice how there's not really a carbon-carbon single bond listed? That's because they are down here at the very lowest priority. Anything on a organic molecule more than just single carbon hydrogen bonds takes priority over it. So if you have a really long carbon chain, yet on this little branch, this small branch, there just happens to be an OH, since that OH is higher priority on this, it would have to be part of your backbone. So it's more important than that first rule we taught you in general chemistry. So what I want us to focus on now is the real rules, or a little bit closer to the real rules, because we're going to add to this as we learn a little bit more, but we won't be drastically changing. So our biggest change, we are finding the parent hydrocarbon, and that is typically the longest continuous chain, which is why it still says that, but it also adds that it includes the functional group with the highest priority. And that is the big change from what we introduced in general chemistry. Matter of fact, we will see that this longest chain rule gets broke quite a bit, because there are plenty times it's better to name it based on something to do with those priority of those functional groups. All right, but for the most part, the rest of it is almost exactly like what we learned in general chemistry on naming-wise. We're just having to add a lot more steps on here for when there are more carbons present. And that's what we're going to spend this first part of this chapter in, is going over those complex rules. All right, so very first thing we're always going to do is just find the longest continuous chain. And something that all textbooks like to do at this point is give you a bunch of examples and actually go out of their way to make them harder to find that backbone. Now, this first one's quite easy, because they did actually make this very nice and pretty, and they went straight across. But on this one down here, this little branch off of it, turns out there's more carbons in it than the rest of this chain. So on that one, the backbone needs to be going down. And that definitely happened down here of the 4-propo-octane. So you're always finding that longest continuous chain regardless. The only time that's ever going to change is if I come over here on this little subchain, if I added one of those things that's a higher priority functional group, suddenly that backbone would actually be more important. So the longest continuous chain only works as the absolute rule on hydrocarbons, or CH will follow a bunch of single bonds. Okay, so once we've identified the longest continuous chain, we actually want to identify just whatever those substituents are. Now, all three of these molecules, they actually made it so the longest continuous chain was going straight across. And so the thing coming off is the substituent. And I typically circle my substituent. I typically box in my backbone. Now, once I do that, once I box in my backbone of that chemical, I actually number my backbone based on where I get to that substituent first. So you notice how on all these, I got this one numbering from the left, yet this one's numbering from the right. That's you don't get a choice most of the time. You want to number it so you get to that substituent with the lowest possible number, which is why we found it at 1, 2. Because had you started numbering at this end, you would have got 1, 2, 3, 4. 2 is a smaller value, so it is the proper way to number it. And that's why they come up with these numbers. When we number that backbone, we want to get to the first substituent with the lowest possible number. And that will apply even when there's more than one substituent. You want to get to the first substituent with the lowest possible number always. All right, so that's where this comes into play. So I have two substituents. My backbone is still straight across. And I have two ways of numbering it because it's a backbone. I could go 1, 2, 3, or I'd have 1, 2, 3, 4. I don't care what the substituents are. 3 is a lower number than 4, so I'm a number with this being the number 1 position. So 3, 4, 5. And now when I fully name it, the substituents get those numbers with them, and then the whole backbone gets that backbone name. So since this had 8 carbons altogether, it is an octane. Ethyl comes alphabetically before methyl, so that's how I decided ethyl comes first. 5-ethyl, 3-methyl, octane. All right, another one that actually creates a little bit of confusion. Let's say excuse me, let's look at this backbone here. We have an odd tie. I have 1, 2, or I have 1, 2. So either side, if I could number either way, I could start with this being number 1, or I could start with this being number 1, and I get to the first substituent at the second position. Since there's a tie, we're going to look at the next substituent. And since I have 2 on this location, I have that substituent and that substituent, this is a better 2 location. So that one's at 3. Oh, actually, that's 3. This is 4. There we go. So I have a methyl and a methyl and a methyl. 2, 2, 4, trimethyl, and then pentane. All right, and on this other one, we're going to do that exact same thing. There's your backbone. We have methyl and methyl and ethyl. And we have 1, 2, 3 versus 1, 2, 3. Since it's a tie, we look at the next substituent, and we get to one more here at 4. But if we come with this way, it would have been 1, 2, 3, 4, 5. So we're going to number from this side and have 3, 4, and 6. And we fully name it, we'll have the ethyl first, 6-ethyl, 3,4-dimethyl octane. All right, now interesting enough, a lot of these structures we skipped, we can actually name now following these rules. So I was gonna do some of that now. Erase that because that's going to be right where I write one of these names. All right, so our strategy is always the same. Since these are just carbons and hydrogens, we're going to find the longest chain. And I do like that 3-carbon chain, so therefore this is just a substituent. And it wouldn't matter which direction I number it. It would be at the number 2 position. So that one is a 2-methyl propane. This one here, that would be the backbone. I could number from either direction, but starting here at 1 is better because I get to that substituent at the 2 position. I numbered here, it would have been 1, 2, 3. So on the 2 position, we have a single carbon, methyl. It is 4 carbons, methyl butane. All right, 3 carbons on this one. I have 2 different ethyls, both of them off that middle position, so it won't matter which direction I number it, that is the 2 position. So I have a 2 and a 2-dimethyl propane. And I know it looks like I'm doing things twice. 2 and 2 and di seem like it is redundant. But it really is done that way simply because when you have dis and tris and whatever the prefix is there, you need to show where both of those are. So every single substituent gets numbered. All right, I'm going to run out of room to do all these, so I'm just going to do a few select ones. So we will do this one, and I'm going to change this ink color because I can't see it too well on my screen. That's better. That's my backbone. 4 carbons in a row is best. And these must be at the 2 position because I got 1, 2 versus 1, 2, 3. So I have 2, 2, dimethyl butane. And let's do this one down here that's actually looks a little bit more crazy. All right, interesting. I'm going to do something kind of weird. I could go straight across and that backbone will work. That's actually perfectly acceptable. But just to show it doesn't make a difference, I'm going to make my backbone do something crazy like this. Because it's still 4 carbons. 1, 2, 3, 4. I just didn't do it a nice little straight line. So I have these 3 substituents. All right, so 1, 2 versus 1, 2. So there's a tie, but this location, this 2, had 2 substituents, so I'm going to have it be the 2 position. So I have these 3 methyls, 2 of them are at 2, one of them is at the 3 position, so 2, 2, 3, trimethyl, and then it's 4 carbons in a row, butane. Now, the remaining ones on here, you probably are going to get a practice chance because I'm going to put them all on the quiz, on your practice quiz on Canvas, where you have to come up with the name yourself. All right, so let's actually take this past that 4th rule to something that's a little bit more complex. And what I mean by a little bit more complex, we're going to actually do something where the numbers do not actually tell us enough. What I mean by that, if we think about this one, the backbone is definitely right there. It's just the 4 carbons, and it must be because neither one of these 2 are carbons. So they must be substituents. All right, but I get a weird situation. I have 1, 2, 3, or I have 1, 2, 3. No matter what, one of the substituents is at 2, one of them at 3, and it's not going to make a difference how I order it. So our 5th tie-breaking rule deals with this, and it just basically says when this happens, when the numbers absolutely do not actually get lower by reordering it, you're going to put the lowest number with the alphabetically first substituent. So since bromine comes first, it gets to be the number 2. And same thing popped up over on this one. There's our backbone, and our 2 substituents are at 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. So it's 3 and 5 no matter what. But since ethyl, alphabetic before methyl, this gets to be the 3 position. All right, let's see, what's next here? The substituents themselves can get more complex as we go in. Now, this is the area of organic nomenclature that's actually got the most developments of recently. So for the most part, it's safe to say your nomenclature rules are the same as they've been since the early 1990s. But branch substituents are getting redone slightly. But what we're going to teach now is the acceptable way. It's just more of, it doesn't handle some of the more complex branch substituents that happen much later in organic chemistry. All right, what I mean by a branch substituent, I'm going to actually draw some bogus backbone. I'm just saying it's something long. And off this backbone, we have had just methyls, and we have had just ethyls. And we could go up even further and say, well, if I put 3 in a row, that must be propyl. And it is. So we have methyl for 1 carbon, ethyl for 2 carbons, and propyl for 3. Well, let's take this propyl group and instead attach it to the middle carbon. So I'm going to actually, instead of connecting here to the end, I'm going to attach to the middle and put both those things off the sides. Well, that is a branch substituent. And obviously they can get more complex because you think about the sheer number of carbons possible, I could make this chain very, very long. So there is a very nice set of rules to actually naming this. What I'm going to do to name this substituent is follow these rules. And that's what we're talking about on these next pages. So I'm going to focus on how they came up the name for the yellow highlighted box here. And what they did was they decided that was going to be the complex substituent. So they found the longest chain in that complex substituent. In this case, it was just 2. And they made this a substituent of it. So if it had been a normal molecule, this is a methyl ethane. We're going to change it into a methyl ethyl. So it doesn't get the ANE end because this, as the whole thing, is considered a substituent. So it's a methyl ethyl. And the 1-methyl ethyl that you see in that name is what we're dealing with on this. And I wrote too much there. I've covered that up. But the methyl ethyl with the 1 in front of it is that yellow box. It's that complex substituent. And then the 4 out in front of it just tells us where in that backbone it is. And they got that from 1, 2, 3, 4. And we would have got the same way coming backwards. Now, obviously, it can get more complex, like I said. You see how this one has four carbons altogether in the whole chain? Well, there's 3 in a row, and there's a methyl off that second one. So the complex name came from calling that the backbone and this the substituent off the backbone. And they just numbered the backbone by saying the first position is what's connected to the chain. So that's where we get the propyl, and the methyl is off the second position there. So that's a 2-methyl propyl. And even on this one, they don't have the numbers to say where they came up with, but what they kind of decided was this is the number 1 on that chain, and we're just going to make that the number 2 and say this was the backbone, and then both of these 2 methyls were little substituents off that mini backbone. 1,1-dimethyl ethyl. Now, we're not boxed in here, but the complex substituent, they decided that this was the main backbone, which means this guy and this guy are substituents. But if you can see, this is a complex substituent because it's not a nice straight line. So this was decided to be that mini backbone with substituents off of it, 2 of them in this case. So we have a 1-methyl and a 2-methyl. So 1,2-dimethyl propyl for the substituent. All right, now something interesting kind of happens on this last example, because what they did was they ended up saying that the backbone comes down here. That makes this thing here a complex substituent. And that complex substituent has 1, 2, 3, 4 things in it with a methyl off the second, which makes a 2-methyl-butyl complex substituent. And I have absolutely no problem with what they did on that complex substituent. But what they did wrong in your book, turns out that longest continuous chain rule, it is more proper, according to IUPAC name, to actually avoid complex substituents when possible. And if I actually called that my straight chain, I wouldn't have had any complex substituents. It's just not necessarily the longest chain, because it's only 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. But the fact that it has no complex substituents is better. So even though this thing is a correct name, this would be better to say that's on the 2 position, that's on the 3, 4, 5, 6, 7. We'd be far better, 1, 2, 3, 4, 5, to say this was properly named 2, 3, 7 trimethyl for the 2, 3, 7, and then 5 for this long thing, which is a straight chain, 5 in a row, pentyl, and then 7, 8, 9, nonane. So I know the rule that we introduced said longest continuous chain, but we want to avoid those complex substituent names when we can. All right, now, something that will help on the complex substituent names, and I'm going to back up to this page. The smaller ones, and what I mean by the smaller ones, we have a few particular, okay, I don't know why that, there it goes. We have a few particular complex substituents that have those parentheses names, and they actually have some trivial names that are perfectly acceptable IUPAC. And all of them have something in similar. That propyl group we already showed that there's two ways we could have it connected, have it in the middle or have it in the center. And while this is always just propyl, and this can be the complex substituent of 1-methyl ethyl, and I'm going to put that in parentheses to stress that that's a complex substituent. Turns out this one is also allowed to be called isopropyl. Isopropyl says the same exact thing. Okay, now 4 carbons in a row have the same type of thing. With 4 carbons in a row branched off of something, just going to get called butyl. And there is an isobutyl, but it's not really connected to the middle. Isobutyl is still connected off the end, but this middle position has 2 carbons off of it. So that is isobutyl. And there are 2 other ways we can connect butyl. So what I could do with this straight chain butyl is move that carbon around and branch in the middle. And I could take that isobutyl and also branch in the middle. Both these have complex substituents names, but this guy up here actually can be called sec-butyl, and this one here is tert-butyl. All right, our next rule is going to cover that whole concept that we just introduced where we can avoid complex substituents. Technically, the 7th rule says that if you can make a pathway or a longest continuous chain that has more substituents, it's going to give you a better name. And that's really evident when we have just the same number of carbons multiple ways. So on this one, I can go from the bottom 1, 2, 3, 4, 5, 6, or I can go just straight across 1, 2, 3, 4, 5, 6. So there's more than one way to get that hexane backbone. But if I had actually left this, the backbone, that guy there is a complex substituent. There's nothing wrong with complex substituents, but if we go over here where we have more substituents, we don't have any complex substituents. So technically speaking, Rule 7 just says we can change where the backbone goes if it gives us better substituents. All right, the weird last thing is alphabetizing. Now, we've been doing this, and I've not really talked about it because I wanted to talk about it now that we've introduced all these weird rules. So when we actually put the names together, we are alphabetizing based on the substituents themselves. So these guys are both methyls, they go together. These guys are methyls, and this one that's up here in the name is an ethyl, so ethyl comes before methyl. Now if you notice, this particular one, we had to put that di in front because they're both methyls. And a lot of people want to do that where, well, D comes before E, so this dimethyl should be first. The reason we don't do that, these numerical prefixes aren't talking about the substituent, they're talking about how many they are. And when we alphabetize, we want to alphabetize by what it actually is. So we are alphabetizing by what it actually is. And that's why E comes before M always. Doesn't matter what the prefix is. Now, that even plays in to these trivial names that we came up with. This is going to be alphabetized by P. Isopropyl will be alphabetized by I. Butyl will be alphabetized by B. And this iso will be alphabetized by I. Now, what's weird is sec and tert. Your book does this wrong sometimes. These should both be alphabetized by the B, though, because sec here is actually because this is a secondary carbon. Secondary carbons are just carbons that are connected to two other carbons. Tertiary carbons are ones that are connected to three carbons. And secondary does mean 2 degree simple and 3 degree simple. So the sec and tert are not letters to alphabetize. We're supposed to be alphabetizing by the B on the butyl. Now, just to actually add some weird things to this. These little prefixes are not ignored on complex substituents. So I mean that by that, if this is the complex substituent, the M is the first letter listed, so this is alphabetized by the M. And if we're on these guys, this one's the one that's most interesting here because it's got a die in front of it. But since that die is part of the name of a complex substituent, on that complex substituent, you would alphabetize by the D. All right, so I want to clarify this rule. It says to ignore the numerical prefixes. You're mostly always going to ignore the numerical prefixes. I'm going to put here, unless part of a complex substituent. When it's a complex substituent, you use the very first letter within those parentheses, regardless of what it is. All right. Now, that's our listing here of the, we already did that. All right, and here is those summaries of those things. So I want to actually, since I have it up here on this page, you're alphabetizing by that, alphabetizing by the I, alphabetizing by the B, alphabetizing by the I, and both these are by the B. Now, all of the complex ones, so the isopropyl, you could name it as if it's a complex substituent. So this is a 1-methyl ethyl. And then you'd put that in parentheses and alphabetize by the M. Isobutyl can also be called 2-methyl propyl. Put it in parentheses and then alphabetize by the M. Sacbutyl looks very similar to this. It's now 1-methyl propyl. Close parentheses, you'd alphabetize by the M. And tert-butyl is also known as 1,1-dimethyl ethyl. Because that's the one, I'd say this is 2. And you would alphabetize that particular name by the D. Because even though it's a numerical prefix, since it's part of a complex substituent, you use it when you alphabetize. All right, we're going to practice this some on various different structures. Now, a much more common way of seeing structures from here on out in most of organic chemistry is our skeletal structures. Skeletal structures are drawing the carbon-carbon bonds only. The hydrogens are intentionally left out, so what we're seeing is just carbon-carbon bonds. Now, most software, like with the software we introduced in lab, if you're trying to draw a structure like butane, that first one, that is how it's going to end up drawing it. You would not actually see the carbons unless you specifically told it to label the carbons. Cycloalkanes are just another type of alkane, but what we're going to do is rip 2 of the N carbons off. This formula here will actually have for every carbon just twice the hydrogens. And we're going to connect the ends and make little rings out of them. And once they get bigger than this, you can just imagine, cyclooctane kind of looks like a stop sign. All right, but we don't see them drawn like this too often. We actually typically draw the skeletal structures because it's a heck of a lot easier to draw a triangle or a square or a hexagon. Now, when we go to name these, we typically see the rules get amended ever so slightly when we start to get more of our functional group changing. And a cycloalkane is slightly different than an alkane. So what the first interesting thing that happens when we have just a single substituent, just one thing off of it, we don't number those. And that's really because it would assume to be the 1 position, so it's unnecessary. So methyl cyclopentane just means you have a cyclopentane with a methyl group on it. Ethyl means you have an ethyl group off of it. Now, this last one is kind of interesting. See how it says the 1 in front of it? Well, that is because they decided not to make the ring the backbone. Since there are 1, 2, 3, 4, 5 carbons over here, they decided that that is the backbone. And the cyclo is a substituent. And the backbone you always end up numbering. So it's a 1-cyclobutyl pentane. Now what's interesting, there really isn't a hard rule that says that we had to name it that way. So I could have actually given this the name of pentyl cyclobutane. And that does happen, but technically in this case that would probably be considered wrong because pentane is definitely more carbons than butane. All right, as soon as we go to 2 substituents, we're going to have to number them. Doesn't matter if they're in the same location or not. If any 2, doesn't matter where they're at, you're going to number both of them. So, like on this first one would have to be at 1, the other one would have to be 2. One of them's at 1, one of them's at 3. One's at 1, one's at 3. All right, there's always going to be ties because you could start at either one being 1, the other one would have to be 3. So if I said this was 1, 2, 3, or I could do 1, 2, 3. So you're always going to use that rule that we put the lowest number with whichever substituent is alphabetically first. So on that middle one I just was talking about, I have an ethyl substituent and I have a methyl. I'm going to put ethyl first, giving us 1-ethyl, 3-methyl cyclopentane. And same thing happened here. That was a propyl group. That's a methyl group. Methyl is going to come first. 1-methyl, 2-propyl cyclopentane. And this one didn't matter because they were both methyls. So one is at 1, the other one's at 3. 1,3 dimethyl cyclohexane. When there are more than 2, what we're going to do is find the best way to get the lowest possible set of numbers. So what I mean by that, if I decided this was 1, and that's 2, I have 2 number 1s, so I have a 1, 1, 2. Had I decided this was the number 1 position, I would have had a 1, 2, 2. 1, 2, 2 is too large. 1, 1, 2 is better. So we take the shortest possible path and try to get the lowest possible numbers. Like on this other one, it's easy to see. I'd probably say the path is either going this way or this way. But since I can do 1, 2, 3, 4, I can see that's going to be better than 1, 2, 3, 4. So 1, 2, and 4 are a better set of numbers. And at no time did I look at what the functional groups were. I actually just got the numbers arranged based on the branches or the substituents that were there. And then I put the name together based on what those actual substituents were. Okay, let's practice a little bit more complex things. So I got what we would consider a condensed structure here, and we want to name it. Now, when you get a little bit more comfortable with this, you might be able to look at a condensed structure like that and come right up with a name. But what I'm going to suggest on something like this is to actually redraw it. And these things that are in parentheses, I'm going to put them above or below the structure and the carbon they're connected to. So they're always connected to the one that's really before it. This carbon has these 2 methyls on it, so I'm going to put 1 above it and 1 below it. And then the very next thing I'm going to is that CH. And it has a CH2, CH3 connected to it. I'm just going to put that above it. And then I'm here to the CH2, CH2, CH, and then I have 2 CH3s, 1 above it, 1 below it. And now I've just turned my condensed structure into something that's probably a little bit easier to see, that backbone. And on this case, yeah, I'm just going to go straight across here, because even though this is 1, 2, and that is 1, 2, having this as my end gives me more substituents. And then when I get here, I'm going to go up. So I have 3 different methyl groups and 1 ethyl group. And I have 1, 2 for the backbone, or 1, 2, but this one has more than one substituent. So I'm going to call that the 2 position. This is 3, 4, 5, 6, 7. So I have a heptane, and I have methyl groups and ethyl groups. Ethyl is alphabetically first. So 3 ethyl, 2, 2, 6, 2, 2, 6, trimethyl, heptane. All right, let's do another one of these. All right, I got a couple weird things going on here because this is one trying to fool us into thinking the straight chain goes right across the top. But on this side over here, I can immediately see that going down has 2 carbons. So that's better than going to the right and just having 1. So that's a better backbone right there. And on this side, I can go straight and get 2 carbons, or I can go down and get 2 carbons. Well, I'm going to go down and get the 2 carbons because that gives me more substituents. And we have that rule that says more substituents is better. So I have a methyl and an ethyl, and I have another pair of methyls. And I have a couple ties here because I got 1, 2, 3, 4, 5, 6, 7, or I have 1, 2, 3, 4, 5, 6, 7. That symmetry gives us a tie, and it's a bunch of ties. Either way, going from this side or this side gives me the exact same numbers for my substituents, but I'm going to go this way and make this my number 3 position because it's an ethyl group, and the other way puts my 3 position at a methyl group. 3, 4, 5, 6, and 7. So full name, 3-ethyl, and 2, 6, 7 trimethyl octane. Ooh, a pure skeletal drawing. All right, each intersection is a carbon, and all those carbons have as many hydrogens on them as we need. All right, so I'm going to just use this to come up with my backbone. So starting at this location, I could go 1, 2 carbons, or I can go up 1 and 2 carbons. Well, if I go up, I'm going to have more substituents, so that's what I'm going to do. So with that, my backbone, I have a methyl, and an ethyl that are our substituents. I'm just going to keep right on going across in this backbone to here. And if I go straight across, I'd have 2 carbons. But if I go up, I have 1, 2, or 1, 2, 3. 3 is bigger. So I'm going to have my backbone curl it back on itself. Therefore, this thing and this thing are substituents. All right. Now we want to number that backbone. And this one's a little bit easier to see because 1, 2 we get to a substituent versus 1, 2, 3. So that's the 2 position, 3, 4, 5, 6, 7, 8. And I have ethyl positions and I have methyl positions, so I'm going to do the ethyls first. So 3, 7, diethyl, 2, 2, 8, trimethyl, 9, 10, decane. All right, got a ring going on here. That ring's got 4 carbons, so it is cyclobutane, and I have 3 substituents coming off that cyclobutane, so I definitely will number them. Since this substituent has 2 substituents, I'm going to call it number 1, therefore this is 2. Now suddenly I care about what they are. I have ethyl groups and methyl groups. The ethyls are going to come first, 1, 1, diethyl, 2-methyl cyclobutane. All right, another ring, 2 substituents. So this is the case where I could do 1 or 3, and I'm going to decide which one's 1 based on the alphabet. So I have an ethyl substituent, and I have a propyl substituent. E comes before P, so it gets to be the number 1 position. 1 ethyl, 3 propyl, cyclopentane. And just to see how this changes, I'm going to take that exact same structure, leave this as an ethyl up here, but this one I'm going to use one of those complex substituents, but we're not going to name it as a complex substituent. We're going to say this is isopropyl, because that's perfectly acceptable to call it that way. Since we alphabetize by the I, still has the exact same name. 1 ethyl, 3 isopropyl, cyclopentane. The other way of naming that, I'm going to put this in blue ink. So the complex substituent, this would be a methyl ethyl, 1 methyl ethyl as a complex substituent. Since that's alphabetized by the M, it could also be called 1 ethyl, 1 methyl ethyl, cyclopentane. Now, on the test, both of these names would be considered correct. And I should have it set up for on the actual test and even the practice test that both those names will be in there acceptable. And if I miss it, I'll get it added to you as you guys are actually working on that practice test. All right, got another one of these. You see what I did here? I did some condensed structures on a ring. So I'm going to start by expanding this ring and expanding this little thing into what it actually is. Because if you notice, it's a carbon with an ethyl group coming off of it 3 times. So it's actually 1, 2 ethyl groups, 3 ethyl groups. All right, this actually has a name that involves a complex substituent, but we're going to find it's actually best to avoid that complex substituent. So our backbone is better to say it is right here. It's just a straight chain carbon with 2 substituents off of it. One of the substituents is a cyclohexane. One of those substituents is an ethyl. And they're both off the 1, 2, 3 position. So we have 3 cyclohexol, 3 ethyl pentane. And even though cyclo seems like it's one of the prefixes, it's not a numeric prefix. It's telling you how the carbons are put together, so you do alphabetize by the C. All right, to do the distinction here, I'm going to redraw this structure. But we're going to do this as if the ring is the backbone. So this is the ring, is the backbone, and this is a substituent. And I'm going to name this substituent as a complex substituent. So I have a 1, 2, 3. So it's a propyl with 2 ethyls off of it. So complex substituent name, 1, 1, diethyl, propyl, in parentheses, cyclohexane. All right, now here's something really interesting. When we introduced the rules and said that if you only had one substituent off the ring, you never numbered it. Turns out, if you give a complex substituent name, you always have to number it. So this particular single substituent, since we chose the name of a complex substituent, we have to put that one out in front of it. All right, another one of these. Looks crazy, looks like it might get a special name. But that ring is just drawn in such a way that was easy to draw. It's actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's a cyclodecane. Most of our drawing software programs will try to get hexagon and pentagon shapes and then combine them however you need it to get the names right. Not how it's not how it's what its actual molecular shape looks like. All right, so these guys are just substituents off of that, and I'm going to number them easy. 1, 2, 3, 4. Shortest possible path. So I have a 1,4 diethyl, and there should be no space there. I just put out too much space. So 1,4 diethyl cyclodecane. All right. Here's an interesting type of question we ask at this time. Sometimes we'll give you names, tell you there's something wrong about it, and want you to get the right name. So 2-ethyl pentane. Pentane is just 5 carbons. 2-ethyl means on that second position there would be 2 carbons. When we draw it out, it might become a little bit more obvious that the backbone should have been a hexane. And that's what we're seeing is wrong with this. The proper name of 2-ethyl pentane should be 3-methyl hexane. How about this one? Isopropyl hexane. Hexane is 6 in a row. Isopropyl here's a weird one. 3-isopropyl is kind of an acceptable name, but what we're getting at here is isopropyl, that part of it is a complex substituent. And what's interesting, I could have still got hexane had I done something like this, and now I don't have any complex substituent. So a better name was 3-ethyl 2-methyl hexane. So avoid those complex substituents when possible. All right, how about this one? 5-chloro 4-methyl hexane. Hexane is 6 in a row. 1, 2, 3, 4, 5. 1, 2, 3, 4. See what's wrong with it? Yeah, it's numbered backwards. Chloro does come before methyl, but it should have been 2-chloro 3-methyl. Dimethyl butane. Turns out this one I can't fix. The butane is simple enough. The 2-methyl is, but it says di. Where's the other one go? Was the di a mistake? Were they both at the 2 position and there was a 2 left off? Was there 3 supposed to be there? We don't really know. There's not enough information to tell us what's going on with that di. That really is why we use both. It seems redundant to have 2 numbers and the dies, or 3 numbers and tries, but you need to have both because they actually confirm each other. They tell everything that's going on. All right, 2-cyclohexyl butane. Butane is 4 in a row. 2-cyclo cyclohexane. Yeah, what's wrong is the cyclohexyl is actually a longer chain, and even though this is a complex substituent, we could actually say sec-butyl, because that's what that complex substituent is, sec-butyl cyclohexane. No number because it's one substituent. 2,3-diethyl cyclopentane. Cyclo with two things. Should they ever be at 2 and 3? No. One of them's at 1, one of them's at 2. Okay, going to pause here because we're going to split this video into 2 parts. That'll give you some time to practice it. Next thing we're going to do is start adding some of our other functional groups to it and seeing how it modifies our nomenclature rules slightly. Because it turns out all of these have a slightly different naming thing based on the substituents. Well, it turns out this one doesn't. That one we just call bromine and we put it in there. But we're going to start with that on the next video.